Okay, good morning. All right, so we're going to add, we have two more tests to go over. Today we'll look at one of them, and on Friday we'll look at the final test that we're going to cover. And Friday we're going to spend some time on going over what test to use and when to use what. So today let's just talk about the new test, and then we'll get there, okay? So this is section 11.6. We're going to talk about absolute convergence and what's called the ratio test. So first, the definition of absolute convergence. So given a series here, the series is absolutely convergent if the absolute value of these terms added together in a series converges. Okay, so it's absolutely convergent if you put absolute value around every single term, and then that new series also converges. Here's an example. If you look at the alternating series with n squared downstairs, and we can tell pretty quickly that this thing is absolutely convergent because if I put absolute value around each of these terms, the minus 1 to the n is irrelevant. And so we just end up with 1 over n squared. And how do we know this thing converges? What test can we use? Right, P-series test. Converges because of the P-series test. So as a reminder, that says that 1 over n to the p converges if p is strictly greater than 1, right? Okay, so here's an example of something that's absolutely convergent. Obviously, this only, if you have just strictly positive terms in a series, if it converges, then it is also absolutely convergent. But with alternating series, things can be a little bit different. And the important thing about the absolute convergence is if we know that a series is absolutely convergent, then it is also convergent. Right? It's automatically convergent if you can show that it is absolutely convergent. So the point of that statement is that now you have another way to check your alternating series. Some alternating series, like this one, you could turn that into a P-series, and just by inspection, we know it is going to converge. So that's another option that you can think about when you're presented with an alternating series. It doesn't work for every alternating series, but works for many of them. Now, the important thing about this statement is that it is another one of those one-way statements. If absolute convergent, then it is convergent, but not vice versa. So convergent does not imply absolute convergence. Okay, we've encountered a few of these one-way statements like the divergence test, right? Here's an example that we've seen before. Here's my alternating harmonic series. And we spent the day talking about it, and we show that it is convergent. Right? But if I put absolute value around each of these terms, then I get a regular harmonic series. Which we know is divergent. So here we have a series that's convergent, but not absolutely convergent. Right? Right. So here's an example of something that's convergent but not absolutely. So think of absolute convergence as a stronger kind of convergence. If that happens, then automatically convergent. Okay? Kind of like all black cats are cats, but not all cats are black cats, right? So here you got your black cats, and then here is kind of like a cat. And if this happens, we say this is conditionally convergent. Again, that means it converges, but not absolutely convergent. So let me write it here. So convergent, but not absolutely convergent. So once again, if you can show something is absolutely convergent, then it is automatically convergent. Okay? And let's find out why that's the case. Why does absolute convergence imply convergence? I showed you one example, but that doesn't prove that's true for every single kind of absolute convergence series. So why is that true? It's actually pretty easy. So here's our regular, just some random series. And let's assume that this AN can be positive or negative. So it could be an alternating series, in other words. Or it could be just be negative all the way through. Something that, it could be positive or negative. If I add AN to absolute value of AN, if both of these are positive, then I just get 2an, right? In fact, 2 absolute value of an. So it can be no bigger than that. And what's the smallest this can possibly be? 0 when they are of opposite signs. If an is -1, for example, then that's -1 and that's 1. We get a 0. So we show that this is bounded between twice of absolute value of an or 0. Now here's an important statement then. If we know this thing is absolutely convergent, then we know of course, by definition, this thing converges. And also by definition, also just because it converges, constant multiple of that doesn't change anything. So looking at this statement here, then, the inequality, that's convergent. This is convergent, right? It's part of a convergent series. Actually, let me write this out. If I put this all in a bunch of series, all right, so now we show that we're saying that, let's say this is absolutely convergent. So that's convergent. This is also convergent. If you can add two series together and it's less than some convergent series, then this has to be automatically convergent, right? It has to be. So must be convergent. And also, by the comparison test, we know this series is less than that. So if that converges, this has to converge. And this is a sum of two convergent series because it converges. Therefore, this has to be convergent. Okay, so if you're wondering why absolute convergence implies convergence, this is the reason why. Another property of an absolute convergent series then you always get the same sum even if you shuffle the order of terms. Then the sum is not affected by rearrangement of terms. So order does not matter. But if a series is conditionally convergent, then the order of terms matters. In other words, if you keep shuffling terms around, you can come up with all sorts of different sum for a conditionally convergent series. But for an absolutely convergent series, it doesn't matter. So once again, think of absolute convergence as a very strong type of convergence. If that happens, then the regular convergence has to happen. Okay? So because it is a stronger type of convergence, if we can have a test that tells us if something is absolutely convergent, then that's going to tell us answer the convergence question. And the test we're going to use to do that is called a ratio test. So let me write it out first, and then I'll talk about it a little bit, and then we'll do a few examples showing that, how this thing works. So three things can happen. And what you do here is you take the limit of the n plus 1th term over the nth term and put it between absolute value. If the ratio turns out to be less than 1, strictly less than 1, then the series is absolutely convergent and therefore also convergent. Okay, so that's the test we use to test if something is absolutely convergent. That's a pretty simple test, actually. Take a ratio, take the limit, look for the number. If the ratio is strictly greater than 1, even by a little bit, then the series is divergent. The last possibility is when it is exactly equal to 1. Exactly equal to 1, then test is inconclusive. In other words, this thing may still converge or diverge, but this test is not sufficient to tell us which case we got. And when that happens, we have to fall back to a different kind of test, perhaps integral test, alternating series test, comparison, any kind of those other tests. Okay, so before we show you how that works, let's talk about why this is true. Statement number 1, how is it that if this ratio is less than 1, we prove absolute convergence and therefore convergence? If you look at this series here, n squared over 2 to the n, and let me write out just a few terms here. First one is 1/2, then it jumps to 1, and then 9 over 8 plus 1 plus 25 over 32 plus 9 over 16. So this thing goes all over the place. Okay, that's enough. Right? It keeps going. This thing is just going all over the place. It's not a geometric series. It's not an alternating series. We might be able to do something like an integral test to show that, but it's still not easy to do. Integrating 2 to the n, that's not easy to do. So, and then you look at these terms. Just by analyzing the terms, we can't really make any determination either. But let's track the ratio. So the ratio between two succeeding terms, going from 1/2 to 1, and the ratio is 2, right? So between these two terms, my ratio is 2. Between these two, my ratio is 9/8. Sorry, 8/9. And then 9/8. And so on. We obviously don't want to keep doing this thing here. But if we keep tracking this ratio, here's what happens if you graph this. So here I'm graphing the ratio an plus 1/an. And down here is n, and the vertical is the ratio. So you see we started with 2, and then we jumped to 8/9, which is right below 1, and so on. So it's going all over the place in the beginning, but the terms are going all over the place. But if you look at the ratio, it eventually kind of settles down around 0.5. And for example, if we go to like 80 here, for example, when you go to 80 and beyond, the ratio is roughly a constant 0.5, right? There's a common ratio of 0.5. Where have we seen that before? What series have we seen before that had a common ratio, a fixed ratio? And we can tell the convergence very quickly. What series is that? Geometric, right. So this is behaving like looks like a convergent geometric series. Right? It's a fixed, almost fixed constant ratio. So we know that everything from this point on is convergent. Right? So if that's convergent, then anything up to the 80th, they're just a bunch of finite terms. If I add a bunch of finite terms to a convergent series, the whole series still converges. So that's the idea behind ratio test. It basically says that if we wait long enough, does that crazy series eventually look like a geometric series? If the ratio is less than 1, then it does. In fact, it looks like a convergent geometric series. In other words, if we wait long enough, we can just chop it off and say that converges, and then we're adding up a bunch of finite sums. The sum, of course, will be hard to find, but at least we can show that it is convergent. So let me write that down. So after n is roughly equal to 80, that part of the series looks like a geometric series. And then everything up to that point, 1 to 79, is finite. So The whole thing must be convergent, right? And if you think about a finite series is always convergent. An infinite series has a different story, but if a series is finite, I only have 78 terms. It doesn't matter what those numbers are. If I can add all 78, I'll get a number out of it. Or 79, yeah. But here's a finite series. Finite series, always convergent. And that's an infinite series, but it looks like a geometric series, so that converges. If that converges, this converges, the whole thing is going to converge. Okay, so this is why the ratio test works. Or at least the idea behind it, to make it, to see if it looks like a convergent geometric series. Okay, now let's do a bunch of examples, and I'll show you how this thing works, and also what happens when the ratio turns out to be 1. So first, a few simpler examples when this thing just works regularly. Here's a series. I'm actually starting at 0, but it doesn't matter, right? I can start anywhere. I can start with any n I want. I happen to want to start at 0. That's fine. The starting point doesn't change the convergence. And as usual, the first test is what? The divergence test, right? And on Friday, I'll make a summary of all the tests, and I'll give you a rundown of what to use when. But regardless of what happens, this is always the test you want to turn to. It's the simplest test. And here, when n grows large, it's going to overwhelm whatever's on the top, right? So yes. If that turns out to be no, then you say that's it, move on. Next. And we have many options. We could have looked at perhaps a limit comparison, maybe an integral test, whatever. But anyway, we're talking about ratio test, so let's use ratio test. So ratio test, we have to find the limit of this. an plus 1 means you go into here, change every n to n plus 1. Okay, so here's my an plus 1. That n turns into n plus 1. That n turns into n plus 1. Now be careful, it's 4 times the quantity of n plus 1. Divided by an is whatever you started with. And let's turn this complex fraction into product of two fractions. So I'm going to have the numerator. And by the way, I'm going to rewrite the numerator. Minus 1 to the power of n plus 1 is minus 1 to the n times minus 1 to the first, right? And downstairs is 4n plus 4 plus 1, 5. And now dividing by a fraction means multiplying by the reciprocal of such a fraction. So that's n 4n plus 1 upstairs minus 1 to the n downstairs. And all of that is trapped between the absolute value. Okay? All right, so now look at this. Minus 1 to the n, these things go away. And notice that the minus 1 between the absolute value is irrelevant. It's always positive. So this thing ends up being just 4n plus 1 over 4n plus 5. Oh, I guess I started with one that is inconclusive. That's okay. Now you'll see what happens. And here, when n goes to infinity, this thing goes to 1, of course. Now the ratio test, this is the third possibility of ratio test. Where is it? Here. Right? When it's exactly equal to 1, inconclusive. That doesn't mean stop. That means go on. Tell me more. Tell me more. I still need to know if this thing converges or diverges. All right. Now what? So the new test fails. What do you think we should do next? What test we should use? Yeah, it's an alternating series, right? So alternating series test is a very, very natural one to use. So we're going to use the alternating series test. Remember, two things that we have to check. First, the terms go to 0, which we checked already, so that's good. Now, the second one, we need to show that if it is less than the previous one. Four n plus 5, less than that. Yes? No? Yes. Yeah. So check. All right, so this thing there, it passes that test. Passes this test. So it is convergent, but not absolutely convergent. So this is conditionally convergent. Okay, so it is a cat, but it's not a black cat. That's what happens here. At least it's a cat, right? You could have something that's not one. It could be a possum. It could be, anyway. And you can try this yourself. Write out a few terms and start shuffling the order. Just write out, let's say, 6 terms and shuffle the order around. You'll find out that as you change the order, more than 6 actually, write out a few more, and then Just shuffle things around. You get different kind of sum depending on how you do that. On page 737 in the book, it actually went through one example where it shuffles the things around. Questions on that example? Okay, let's do more. N times 1/4 to the n. As usual, let's do the divergence test first. Okay, so now what happens when n goes to infinity? This is infinity, right? And what's 1/4 to the large number? Close to 0. What's that equal to? No, it's not 0. It's indeterminate. It's an indeterminate form. We don't know what it is. And what do you do when that happens? L'Hopital's rule, yeah. But you know what? Let's just do the ratio test. It's not that hard, right? So if this thing tells me something that, and besides, even if I show this to be less than, even if I show this to go to 0, I still need to do the ratio test anyway, right? So this, one of those cases where this first test is trying to tell you something, but you have to do a lot more to get the answer out of it. So okay, we can do that, fine, but why don't we just do the ratio test? So much work. Let's do a ratio test. It's not a whole lot of work. It's a limit of 2 terms. That we can do all day. All right, so once again, change every n to n plus 1. Divided by just the generic terms by themselves. So usually you want to group things that look alike together. So let's put a fraction of just these 2 things together. And then 1/4 to the n over 1/4 to the n plus 1. And I'll do that same thing I did earlier. Break it up like that, right? And then we throw these out. Okay, now when n goes to infinity, what does this do? 1. 1 times 1/4. That's 1/4. Which is less than 1. So this thing is absolutely convergent. So in other words, this looks nothing, it kind of resembles a geometric series, right? But here we have proof that after a little while, or after a great while, it'll start to look like a geometric series with a common ratio of 1/4. So therefore it converges. So this is absolutely convergent, therefore convergent. It's a black cat, therefore it is a cat. I don't know why I'm saying that. All right, so absolute convergence, that's it. This is a very, very simple test. In fact, on Friday, I'll tell you, emphasize more, but consider using the ratio test as your go-to test when you're given just a random series. It has a chance to fail, as we saw earlier, so you still need to know all the other tests. But it's a very simple test. Consider using that as your go-to test. Here we have, I'm going to start at 2 here. Why can't I start at 1? Yeah, log of 1 is 0, so I can't start with a 1. I have to start at 2. But it doesn't matter. I can start anywhere. Okay, take 3 minutes and find out if this thing is absolutely convergent, or conditionally convergent, or divergent. So 3 minutes. So find out if it's absolutely convergent, conditionally convergent, or divergent. Okay, that felt like 3 minutes. So is this a black cat, a cat, or a dog? Raise your hand if you think this is absolutely convergent. Absolutely sure? Okay, raise your hand if you think this is conditionally convergent. Okay, divergent? Okay, most people chose conditionally. Let's find out. If we use the ratio test, by the way, this passes the divergence test, right? This goes to infinity, goes to 0. Good. So let's go ahead and use the ratio test. So what happens when you do this? What do you get out of it? Those of you that said this is conditionally convergent. What did you get out of this? Did you get a 1? Yep. Yep. You should get a 1. Right? The minus 1 to the n, these go away. So this ends up being natural log of n over natural log of n plus 1. And when n is large enough, the plus 1 is irrelevant. Natural log of 17 trillion and 17 trillion and 1 are the same thing. So this goes to 1. So inconclusive from the ratio test. And what's your fallback test? There's not one right answer, right? What's an logical you want to turn to next? Alternating. This guy is alternating. Alternating series it is. So alternating series test. Well, this goes to 0, so good. And we also know that 1 over n is decreasing function. Because this thing is monotonically increasing, therefore the ratio is monotonically decreasing. So passes. Therefore this thing is conditionally convergent. Okay? So there's the CC. It converges, but it's not absolutely. Let's do one more example. Let's put a trig function in here, sine. How about this one? You know, in your series, a trig function is actually a pretty good thing because we know these things are bounded, minus 1 and plus 1. So a comparison test could be used here. But of course, you can use anything that you at your disposal. All right, let's see. Does it pass the divergence test? Yeah. Again, sine is bounded between 1 and minus 1. And this thing just keeps growing. So eventually this goes to 0. So yes, it passes the divergence test. We have to look further. So let's do our ratio test. Change n to n plus 1. And notice I just went ahead and split up the complex fraction by taking the n plus 1th term multiplied by the reciprocal of this thing here, because we're dividing by that. Again, group things that look alike. Let's put the sign stuff together. And then the factorial terms. Let's start with n plus 1 factorial. So first of all, do you see why I can rewrite n plus 1 factorial as n plus 1 times n factorial? See that? Does it make sense? Because n plus 1 factorial is n plus 1 times n minus 1, n minus 2, dot, dot, dot. And all of these guys are n factorial, right? Upstairs we have our n factorial. And here, when n is large enough, once again, that plus 1 is completely irrelevant. sine of n plus 1 pi and sine of n pi, when n is sufficiently large, doesn't matter. Same thing. So this will be either 1 or minus 1, because sine is changing sign between these two. We have to stay away from when sine is 0. But because we're taking the ratio, it's small number. So basically, it doesn't matter even if sine becomes 0. It gets close to there and then gets canceled out. So this will become 1, basically, or plus or minus 1. And we're taking the absolute value, so the sign is irrelevant. We end up getting 1 over n plus 1. And this goes to 0. And it's less than 1, right? We just want it to be strictly less than 1, and we have that. So this is absolutely convergent. It's the blackest cat you have ever seen. All right, that's it for today. See you again Friday.